thank you for attending. So just a public announcement first. So during the talk, please make sure your phone is on silent. As well, if you want to give feedback about the talk or talk to us after, you can do so outside after it's finished. So I'm going to introduce myself. So I'm Cédric Caillot. I'm a lead physics programmer at Epic Games. Today with Jim Van Allen, we're going to talk about chaos destruction in the latest UE5, especially talking about how you can improve the quality of your simulation, and as well talking about performance. So this talk will not talk about like how you fracture or you cluster, how you set your collision. There's plenty of resources on the Unreal Engine dev website. We will assume that there is an asset and that it may not be performant, and then we'll talk about how you can make it performant. And then Jim will then, in the second part of the talk, will basically discuss how you can control and have some more artistic intention on how you use the geometry collection asset and for this. First of all, I'd like to, even though we're going to not talk about how you fracture, cluster, make your collision for geometry collections, historically, geometry collection have been created using the fracture editor in Unreal. We're slowly moving to introduce new set of tools like non-destructive workflows. I encourage you to look up those links and to discover what it is about. You'll certainly hear more about this piece of technology in the months and years to come. Just as a note, so the assets in this talk has all been set up using Dataflow. So let's start talking about performance. So this is the type of asset we're gonna be using for this talk. So this one is like, straight from ZBrush, or like a 3D scan. It's about like 1 million polygon. It's been fractured. And then you assume that you got it set up and it works fine in isolation in your little test that you've done so far. And it's been in the content browser, ready for your level designers to use and play with. And now they use it everywhere. And then, so you get like something like that. You get like 32 of them. And then your frame rate is like, even if before anything is broken, it's like sub 30 frames per second. And then as soon as you start breaking things, your frame rate tanks. And people start talking about, we should reduce destruction. We should not have as much destruction in the game, or maybe even not have destruction at all. And we don't want that. We all love destruction. So everything, yeah, it's painful to watch. So we're going to start like looking at first the rendering part of the performance. And so we're going to talk about like 2 simple changes. Enable nanite, or at least we're going to make sure we have nanite enabled on the asset. And then we're going to use root proxy. And I'm going to go in details in the next slide about how we do this. So you may say, well, if you have an asset like this, you should have nanite enabled, but maybe when the project started and this asset was introduced and made into a geometry collection, nanite was not enabled, and especially not for this particular mesh. And now you're like, oh, I need to go back and refracture, use the fracture editor and redo everything when I really like this, the way it's like fracture now, and I need to redo all those things. Luckily, geometry collections have a flag that you could just enable directly on the asset and say, please use, nanite. And so it can be done post fracture, so you don't have to redo everything. So the benefits of using Nanite as well is that you're going to get the auto load using Nanite clustering, because by default, geometry collection rendering doesn't support LOD. So that's a limitation of geometry collections. So by using Nanite, you get that for free. The other benefit is that Nanite will be the Nanite like mesh, and data is going to be cooked into a very optimal format using geometric compression. And then so you can then remove all the geometric information from your geometry collection. And so for that, we have a little checkbox that you can use, and it's going to make your assets very, very small compared to what you would get if you would keep this information in it. I'm talking about like you can get 95% reduction in size of the geometry collection asset. So root proxies, it's fairly new. It's been there like for about like 2 releases, but it's been more usable in the latest ones. What it is basically, it could be one or multiple meshes that you can use in place of the geometry collection until it's broken. Usually, historically, I guess it was used, you could set it up into a blueprint. You'd have your mesh component and geometry collection component and some kind of logic when you detect the first break, and then you would switch from one to the other. It was like a bit of a pain to set up. So now it's all natively set up. So you don't have to listen to break events. You don't have to do blueprint stuff or anything like this. It's completely supported inside the geometry collection component. So it supports, of course, because this is mesh, you have like LOD, Nanite, Lumen, all the things that you like and love in Unreal. It also runs in the editor as well. So if you have like very large in the editor, it can be very slow to kind of go through your level. But with this enabled, it's like way more performance. We have introduced also like custom renderers in geometry collection components. And then so if you choose the geometry collection root proxy renderer, that's a mouthful, then all the root proxies will be rendered using an ISM that is automatically instantiated for you. You don't have to set up anything else. And your root proxies will be instantiated across the entire world of the game. So very highly recommended. This is used actually in Lego Fortnite for reference. So yeah, good example, glass. Because if you use just the geometry collection as is, you're going to see all the internal faces and everything, and it's like, it's not great. And then if you use a root proxy, you can have your pristine mesh with no internal faces, and then it's going to start showing only the interfaces as soon as like the mesh gets, and the geometry collection gets broken. Little note I didn't specify there, just come to my mind. The collision will always come from the geometry collection, never from the root proxy mesh. So if you have collisions set up on your root proxy mesh, it won't be used for collision. Only the collision from the geometry collection will be used. There's a limitation right now in 5.5. It has to use the same pivot points as the geometry collection. This has been fixed in the dev branches, and it won't be a limitation anymore in the next release. So now that we've taken care of the rendering part of things, another big element is the number of rigid bodies and how long they live and they are active in your scene. And they can have a tremendous amount of effect on your performance. So for that, there is a quite of unknown feature whenever I talk to people about it, which is called remove and break. So remove and break is, you can find it in this little tool. Like it looks like a little trash can, so don't be afraid of clicking on it. It won't delete anything. It's by doing so, you can then select each individual PCs and by groups and kind of like assign different like metrics, timing metrics for your PCs. So the metrics are how long after it got broken from its parent is going to be start to remove, and then how long it's going to remove. So there's a min-max timer. It's like it's going to randomly assign a time in between those two limits. It works with the scatter feature. So the piece will just kind of like eventually kind of like scale down to nothing, as you can see on the screen. And there's also another feature called cluster crumbling, which means if you have a very large piece of cluster that falls on the ground but hasn't broken into smaller pieces, after it broke, you can ask it to, by checking this box, you can ask it to further break down into smaller pieces so that like not large pieces are basically scaling down, but just only the smaller ones. Very useful. Highly recommended to use it because it's like you get a lot of artistic control with this, and they give you a lot of control about how many and how long like those rigid bodies stay around. So the little sister that is well more known, like little sister feature, which is a remove on sleep. So this is the kind of the same, but it's basically per asset. And you can say after sleeping for 3 seconds, then please disappear. You can also kind of control this like sleeping state by setting some kind of like velocity threshold. Doesn't have as much like artistic control, but it's worth like noting that it can be still useful in some case, depending on the scenario. But I would still highly recommend start from the remove on break. Definitely a better feature. On top of all the removal feature that I just talked about, we have some extra controls. So we have this removal timer multiplier. So it's a settings. It's a console variable. Because it's set in, you can set it in a config. You can set it per platform. So it could be nice. For example, you set all your assets. You say, oh, between 5 to 10 seconds, like start, making things disappear. But then you have now this low-end platform you need to support, and you don't want to go and create like new asset for that, or you don't want to just readjust all your settings. So it could be like a late in production kind of like a decision. And then so you can basically use this multiplier per platform, and your low-end platform basically has a multiplier that makes like things disappear faster. So it's a great way to kind of like, create one asset that kind of runs on different platforms like nicely. Another one, another nice control is like per component. You can also control whether you want the removal feature to be enabled or not. And those one can be set as well as runtime, so it's useful. And case where you may need it could be you have this one asset that's been optimized to get rid of like the fragments at runtime, but maybe for this like cinematic scene, maybe you don't want it to do that. So you could just, for this particular instance, like disable it. So this one doesn't have any video. I'll try to explain how this works. One big part of performance problem you can get with geometry collection is you get a lot of stuff that start piling up. And piling up means collision detection. And then geometry collection are often made of convex, which is not like the fastest shape to basically collide with. And then so if you really want to have a lot of destruction, I recommend using this one. So you could say, for example, for all the debris level, let's say level 1 or 2 in your hierarchy, you may want to set it one-way interaction. So one-way interaction means if you have a one-way object and a rigid body versus another one-way rigid body, they're going to collide like as they were spheres. So it's very efficient. It's like sphere-to-sphere collision is like literally like the most efficient we can have. And then if it collides with a two-way, then it's going to collide as if the two-way was like infinitively massive. And then so it won't affect it, but then it will be affected by the two-way one. So those debris basically become kind of like, they react to the world, but then they don't really affect the world back. Also, like they don't apply damage on top of the existing damage, so you don't get this cascading effect. So it can be really nice if you get a lot of destruction but a lot of those little debris that basically just like get in your way. You can just like enable that. It's very useful. By the way, that's a feature that also exists on normal rigid bodies. So you're out of sight of geometry collection, so it can be useful for other things. And it's kind of hidden because it's another checkbox in the long list of properties of those components. when all those things have failed to get you where you want to be for performance, you can use some extra things like those console variables. So what they allow you to do is that maybe you don't really know how much destruction you can get at any point of time because user takes the decision to destroy things or not, and you have many players, and there's unknown that you can never plan for. And then so you may want to say, you know what, I'm going to want to only have 10 clusters that can break per frame. And then so this console variable allow you to do this kind of stuff. So you can set it so you say 10, and if you have 20, then there'll be 10 clusters that were supposed to be destroyed at this frame. They will be destroyed at the next frame, and then they will have the priority over the other ones. And then if not, then they will be rescheduled, and so on and so on and so on. Usually, you can set up a limit on how many times it gets rescheduled, but usually this value, we have found that it's you don't have to set it. You can leave it just the way it is right now. But I encourage you to play with it. Each project is different. Each scenario is different. So those are tools that are available to you to kind of find the sweet spot in what you want to achieve and what you want, where the performance is. Be aware this kind of changed the behavior, because if you have a lot of destruction that would have happened in one frame, you would see a lot of things happening at the same time. Now, because you get rescheduling system, then you see those kind of rippling effects. So be aware that may change the behavior of your destruction. That said, if you have a lot of destruction, there's too much going on for the players sometimes to notice. So same, I'll leave it to you to decide if it's useful or not, and if it's something you want to use. Right now, they are console variables. We intend to expose them as project settings, so it's going to be more accessible. We understand that there is way too many console variables in Unreal. So I'm going to talk about damage propagation. This has been there for a while, but we never really talked about it. This is great to. This was introduced. Okay, let me rewind. This was introduced as a kind of an artistic control and to kind of emulate how energy propagates and is absorbed by a material. Not simulate, but emulate. It's really a simplified version. But you can get great effect with it. So there's two parts. There's the break damage propagation and the shock propagation. I'll explain those two. So break damage. So each piece has a damage threshold, let's say 100. And then you got this thing that comes, and then it has a damage potential of 200. Then I'm going to take 100 out of it. It's going to be left with 100. So that's the left energy after the break. And it's going to propagate through, you see the connectivity graph there, between the pieces. It's going to propagate to the pieces around. And then it gives the opportunity of the pieces around to basically break, because there is left energy to break something. So if you throw something very hard at it, if you throw something not very hard, one piece won't break. But if you throw something very hard and you have a high damage propagation, then it will just propagate through the piece. I'm going to show you the example of that. That's the video on the right. So this is no propagation at all. This is half of it. So it's exactly the same projectile and velocity and everything, and this is IO1. So as you can see, each step produces more or less rigid bodies. So that's something you can use as well as a way to control your destruction and the amounts that comes out of it. We have a shock damage propagation. If you use level base damage threshold, every single object inside the same graph, basically in the same connectivity graph, will have the same damage threshold. So shock propagation will do nothing, because shock propagation works in a way that if you have 50 and then the damage threshold is 100, then what's going to happen is there is not enough energy, and then this energy will be then shock propagated to the neighbors. But then if all the neighbors are already 100 as well, they will never break. So it's useful in situation where you can set your damage threshold to be based on the size of your PCs or different metrics if you even like go there. And then so that's why like using site-specific damage threshold is like somewhere where you can have a better variety of like damage threshold and where shock propagation may be more useful. So the larger piece doesn't get destroyed, but then it propagates to the smaller piece, and then your smaller piece then breaks. So it gives more natural looking kind of destruction where the intuition is that things break where there is a weak point, and then smaller piece will be usually those weak points. So same, play with those numbers, see what fits you, and have fun with it. Lastly, another great tool to deal with a number of rigid bodies is the Tiny Geo tool. So Tiny Geo tool allow you to kind of select things by their size, and then you can do several things with it. Usually those little things they're not great for multiple reasons. First of all, they're very small. They don't really contribute to the overall visual quality. They can have like very weird kind of like collision shapes and act very weirdly. They kind of like bounce in all direction and everything. They get stuck under the larger ones and cause like the top rigid body to never go to sleep because there is always a fight between those two. So what you can do, you can select the small one for a bolt. Sometimes you can just delete them, which is nice. I mean, especially if they are like internal to your geometry creation, nobody's going to see it, and it's going to reduce the number of rigid body. Another thing you can do is like you can select those ones and then set the remove on break to be kind of instantaneous. You can set it to 0, 0, and then as soon as it breaks, it's going to just like pop out of existence. You just replace that. You have a break event. You replace this with like some Niagara particles, and then here you go. So yeah, just an example there. Just by removing those. Oh no, those ones have been merged actually. Yeah. So this is you can also merge them with the closer clusters. And then so we go from 329 pieces to 219, so that's a lot less, like a third less kind of rigid bodies, and for like very little, basically, difference. So very useful tool. Yeah, make sure you use it. So that's it on my side. I hope you learned something. I'm going to now give the microphone to Jim, and then he's going to talk about how you can control destruction. Yeah.
Thanks, Cedric. My name is Jim Van Allen. I've been a technical artist at Epic Games for about 6 years now, specializing in destruction. Before that, I worked at Industrial Light and Magic, working on movies like Pacific Rim and the Transformers movies. And so I've been doing this stuff for a while, and that was a lot of fun working on the movies, but this is really fun stuff. This is, I love doing this stuff, and I'm excited to share some of it with you. I'm going to cover a few things that are like very specific and kind of niche, that if you're not using Chaos, it will be boring, but hopefully bear with us. We have some other things that are more broad concepts, and then some goofy stuff at the end. So the first one is talking about anchoring. In the initial release of Chaos, anchors had to be set through a field, which was great. It works fine, and it still works. But you have to manage this other thing. You have to do some clicks, which I hate doing clicks. And they're fine, but they're just not they're not easy to use. They're not intuitive for an artist. Let's be honest, artists are pretty lazy. So this one, now in fracture mode, you can right click on any bone and you can set it to be anchored or kinematic. And we've changed the way the anchors work. The anchor fields work the same, but anchors now will break when force is applied and just release the whole object. Kinematic objects stay the same. So hopefully that's pretty obvious. One note here, if you're an effects artist coming from Houdini or some of the other packages, a lot of people have the instinct to set things to sleeping and just ignore kinematics or anchors. That doesn't work as well in our system because you still pay the cost of having those objects in your scene, even if they're not simulating. And you also have a risk of them getting knocked and they get bumped over, and then everything starts simulating and your scene's really slow and you're like, chaos sucks, but but that's not the case. It's actually just don't sleep. We don't recommend using sleeping. So this is physical materials. I have to click this one to get started. So a really common note when you're working on destruction is to make things look heavier. It doesn't look like stone, it doesn't look like concrete, so on and so forth. And so a lot of people's first instinct, including mine, is to find the physical material and increase the mass, increase the density, and it should be awesome, right? Well, no, it's not. And the reason is we don't have any kind of air resistance, and gravity affects everything the same way. So as you can see here, these three different objects with outrageous densities all behave basically the same. This one is not the right one either. It's just showing how they interact with each other. And I just put it in there because it's fun. But like, so my super lead is like, that's like the sun basically. And the stone is if you accidentally entered 2000 instead of 2, which is 2 is the correct value, 2000 would be kilograms per meter cubed. So it's just a really easy place to make mistakes. And it also shows you how your brain will totally lie to you. And it's very easy to get lost. And so I really wanted to emphasize that because this is something that's happened to me where there was a short time when physical materials were broken, they weren't working at all. And I'm like sitting there dialing all the settings and trying to get it all just right. And I'm like, this is almost right, but it's not quite working. It wasn't working at all. And so it's just something to be aware of. If you're having trouble in your sims, don't necessarily jack up the density. And also, if things are starting to go crazy, you might want to check the density and see if an artist has gone in there and done something foolish. So the way that we get things to look heavier, I'm doing here is by adjusting the friction and the restitution. And so with the super lead over there, I've got the friction up to 1, I think, and I set it to max, and I set the restitution very low so it doesn't bounce. And so that's how you really want to dial in the behaviors. Another thing is the amount of forces you apply. And so if you're applying an extreme amount of forces, things are going to go crazy and they're not going to look heavy. So you can reduce the amount of forces you're applying in your projectiles or weapons. I'm glad I put this note in. Another thing I need to mention is down here at the bottom, there's a thing called a damage threshold multiplier. And that is kind of a secret weapon for increasing your damage thresholds from the physical material. And I'm going to talk about that here. And so what that allows you to do is you can control the behavior of every asset in your game with just a few physical materials. And so this is what we did on the Lego project. This is what we'll do on every project from now on until forever, because it's just really easy and you can have hundreds of assets all over the game and you can go in and say, okay, the stone's being a little wonky, open it up, adjust some settings, and you can even change the damage threshold multipliers up and down and get the exact behavior you want for everything in the game. You can also go to a specific asset and adjust its settings and it'll still get that multiplier and be controllable. So you can still have explicit control while having this overarching thing. So the lesson for physical materials then is your eyes will lie to you, but they can control everything. Okay, next one is, I'm going to talk about projectiles a little bit, because I'm not sure how much of this we've communicated out to people. This is spawning a master field using a trace, and this is what we have in our content examples and in the Lyra project, if you check that out. And it's really cool. I love fields. They're like my favorite. You can get exact control. You can do anything you want, but there's a problem. They're slow. They're heavy and slow. And so if you start using them, you're going to get great results. Everyone's going to love it. And then somebody's going to come along and say, oh, it's all these milliseconds. So many milliseconds. And you'll have to cut it. So we don't want to do that. So an easy solution to this is to use a new node called, I can't read it, apply external strain. There we go. And so this basically does the same thing. We're applying an external strain to force a break, And then we have an extra node called apply braking linear velocity. That is applying a little velocity based on the normal from the trace. So it's pretty easy, super easy to set up, way easier than setting up a field. And it's pretty powerful. It's not quite as awesome if you're an artist and if you're trying to do something really cool or really specific or a big hero thing, I would use fields. But if you're using weapon that's in the game that's being used constantly, this is a great solution. I should mention you can also add internal strain if you want things to be decremented over time and cause damage to happen over time. And we also have a node for applying braking angular velocity if you want to add a little spin. I find that I usually don't need it because once they brake and start having the velocity, they start bumping into each other and rotating anyways. So this one is surprisingly exciting. This is just using collisions. This is no fields, no strains, no nothing. And I was going to show you how terrible of an idea it is, but it actually works really good. This is the dream, right? This is, you just drop everything in your world and just start wrecking things. You don't need me. You don't need level designers. You don't need anybody who's specialist. You just start doing your thing. I don't really have anything negative to say. It works really good. So this is cool. This is exciting. I kind of feel like it's like riding in a self-driving car, though. I did that for the first time last night, and it's a little scary. It can be a little consistent. Ours ran a red light. No, it really did. And so it's great. It's awesome. It works, but it doesn't always work. And so if you have things like you have a gate that the players have to destroy no matter what, or if you are increasing the speed of objects, sometimes you can have objects pass through, you're not always going to get a hit. So if you want to always get a hit and still have it look cool, we recommend using collisions and then also adding external strain command as well. This will always hit everything, and it gives me the artistic control that I love. And so in this example, what we're doing is we are increasing the size of the external strain and the velocity that we're applying based on the velocity of the projectile. So when they start off, they just bounce off, and then here towards the end, they're really moving. They're applying a much more strain and much more damage and more awesomeness. And so it's also worth, sorry, I'm checking my time here. It's worth giving a note here that, when you're doing this sort of thing, we want it to be realistic, but what we're looking for isn't necessarily that things look real. We want it to look like you think it looks real. And more importantly, if you're in production, you want it to look like the supervisor thinks it looks real. And so we have all these tools. I highly recommend starting with real world numbers and going from there. But as you have to adjust things, these fields are great in applying external strain, and these sort of things give you that explicit control to really give you nice, satisfying results. Okay, next one, Niagara Data Channel. Not sure how many people have heard of it. It's experimental in 5.5, but this is the future, so at least as far as I can tell. And so there's, math reasons and performance reasons of why Niagara Data Channel is awesome. Facilitates communication between chaos events and Niagara systems. But what's really cool for me as an artist is, it puts the Niagara system in my destructible blueprint. So it's there. I don't have to go find a node and select it and do more clicking. It's just there. It's easy to get to. And what's really exciting, for me at least, is this last bullet, which is that we can pass variables through to the Niagara emitters. And so what we're doing here, let's see, what are we doing? We can control the count, the scale, the color. We have some other stuff. And so you really can start to control your Niagara simulation from the chaos simulation and start doing exciting stuff. And so in this example, particles are being generated by a chaos break event, and then we're immediately removing them on break. And then what are we doing? Oh, right. So I've stepped ahead. I started reading the bullets. I should have started with my own head. But down here at the bottom, you can see in our construction script, we're getting all the data that we can get from the geometry collection and storing it into a struct. And so we're getting the IDE, we're getting the volume, we're getting the mass, we're getting just everything we can possibly think of, we're getting the transforms. And so what happens is when the piece removes, it creates a chaos removal event, and then we send that, or actually, no, we're doing on break, I'm sorry. But you can do it on either one. So we're doing on break, the piece gets removed completely, and what we're doing is we're filling that missing volume with a bunch of boxes in this case. Let's see if I missed anything. And so we have that, and that gives us a chance to do some more cool stuff. And so in this example, all of these red particles are the ones that are being emitted from pieces that have been removed. And if you've done much rigid body simulation, you know the most difficult part of any rigid sim is those first few frames when things start to break and everything's interpenetrating, everything's colliding, and it sucks and it's not fun. And it makes your sims blow up and all these sort of things. It makes everything slow down. And so by doing this, you kind of just get around a lot of that. It's not a magic bullet, but you can't tell the difference too much. Let's see if we go down to this one. Okay, you can kind of tell the difference. I exaggerated a little bit, but you can't tell the difference too much, and it gives you the really nice effect, and it just gets rid of all those annoying little pieces that are going to give you trouble. And then over here in the little image off to the side shows the variables I ended up passing through to the system. So we're passing smoke color, large debris color, small debris color. We have a use NDC box, so I can turn off effects completely if I want to just test other things out. I can send my count through, min and max, and a scale min and max. I also have a fun thing that doesn't 100% work, but that's okay. The top one about the min size. So what I'm doing there is when I do everything in the construction script, I'm comparing the ratio of the sizes, and then everything above that size that gets removed gets the larger particles emitted, basically. So anything small, we're not emitting the larger particles, we're just ignoring them. And then we have our video that will show if we can use a computer. So funny thing about this video, and I hope you remember back at the beginning, Cedric's video where we had, what, 20 pieces that were running really slow. This is 150 objects, and we're just going full ham on this. This is all the settings that we've talked about in the talk so far being operated. And the funny thing about this video, the video runs too slow in PowerPoint. PowerPoint can't even handle this many. I don't know. It doesn't make sense, but we had to like flip over because it's too powerful for the video. Yeah, and this whole time, so I can just destroy these. I can be close. I can be far. I can just go and go and go all day. And it never drops below 30 frames a second. It's usually around 40, 45. There's some things that start to slow down if I destroy every single little piece, and I haven't diagnosed why that's happening, but it's pretty cool, I think. So, yeah, let's see. And then if we go back, let's see, computer. And so then lastly, I wanted to talk just for a minute about a fun thing that we came up with for, this was for Lego Fortnite. It was very late in the project, and some wise guy said, hey, what if the Lego things build themselves when you place them in the world? And everybody said, no, that's a terrible idea. We don't have time. We can't do it. It's impossible. Actually, it's not impossible. There's a lot of ways you could do something like this, but nobody had time. And so they're like, Jim, why don't you go and see if you can do something? And then when you fail, we'll tell them we can't do it. We taught them. We found this node, I believe Cedric probably wrote it, called get initial local rest transforms. This is in UE5.5, so you can use it today. And what this does, and it's really awesome, is it just gives you a list of all your transforms for every piece in your geometry collection. And so once you have that information, you can start doing fun stuff like this. So this, all we're doing is let's see, I have a little chart. This is part of the blueprint. It's a little, so I don't know if I had the note about it's not fast. So sorry, it's not fast. So what we do is we get all those initial transforms, which is our final position. We just move everything up with some randomizing, blah, blah, blah. Move it all up out of the way. And then we set that. We use the set local transforms command to make that be our starting position. And then we just lerp the transforms. And, we got all these like little, one-off objects, cases and whatnot. But really all we're doing is just lerping from the ones that are way up high to the ones that are in the final position. And it works great. It's awesome. It's not super fast, like I said, but it's really easy and cool way to start doing some interesting things. And that's what got me excited. And then on the Lego project, what we did is we did this. Obviously, we're not going to ship with that. So we gave it to somebody who's smart. And he took it and made it into like a real C++ thing. And now it's in the game. And so anytime you place a thing, and it's awesome. So it's really cool. And it was really easy, which is really rare that you get something that's easy and you look cool. Everybody thinks you're smart for a few days. And the only cost is, so we're not simulating anything. All we're doing is moving the pieces visually. So it basically is free, at least for me. This is another example. So it's like, okay, we can do this. So what if we did something more fun? So this is just making a little tornado that builds itself. All we're doing is setting X and Y to be the sine and cosine of a random value and then multiplying it times Z. So nothing super complicated if you've done this kind of work before, but it's super fun. And honestly, the reason I'm showing you guys all this stuff is I hope somebody out there goes and does something really cool. Please let me know if you do, because there's so much potential here for doing interesting stuff. This is another one. We just put a thing in sequencer and animated it back and forth and said, okay, well, what if we push the pieces out as it goes through? That was pretty cool, pretty fun. This one is actually useful. I'll skip to the bottom. Spoiler alert, it's not fully implemented yet. We don't update the collision. So if you actually break this, the pieces will snap back to their regular thing. Hopefully we'll get that fixed pretty quickly and it'll be awesome. But I mean, gosh, this is awesome. So all we're doing is creating a collision event. When the collision happens, we're just pushing the pieces in. We're just by everything within a radius of the sphere, a little bit larger than the size of the sphere, we're just pushing them in. Super easy. And for me, super cool. I love this kind of stuff. So I was doing that, and I love it. It's so fun. And then I started thinking, you know what I hate doing? One thing I hate doing is ground simulations. If you've done rigid body sims, they're just the worst. They're just not fun. They're not the hardest thing to do, but they're like the most annoying thing to do. Because where does the ground go? If you haven't done this before, you got to put the ground somewhere. You got to have something for things to collide into. And it's not fun at all. And so this is a technique I actually developed at my last job using completely different tools. But now that we can use the set initial rest transforms, we can do stuff like this. And all it's doing is moving the sphere through the volume, or yeah, through the volume, and we're getting, I think we're getting, no, we're just doing it based on the position. We're not doing any collisions or anything fancy, and we're just pushing the pieces down and then we're rotating them. But wait, there's one more. Let's see. And this is the one I'm most excited about. Oh gosh, it got moved over. So sorry about that, but you can still see what's going on. That is weird. Anyways, we'll just roll with it. This is the exact same blueprint as the other one, but this ball is dynamic. It's still not colliding with the with our ground plane. It's colliding with the ground underneath. And then what I did is I used another trick that I did at a different company, where we basically have created a field underneath our geometry collection that increases the damping as the ball enters it. So based on the Z depth or the Z position of the ball, we increase or decrease the amount of damping applied, and so it forces the ball to roll to a stop. So I just wanted to show you guys that stuff. I think it's really fun. And as we continue to develop, I think we're going to be able to do some really, really cool stuff with it. So, and thank you. So.